So good morning, this is Deep Generative Models. So today we are going to talk about how to actually write code using GPT to generate text. So in previous weeks, we have covered how GPT works and how transformer works in general. But you may think you kind of understand how the models work, but you are not entirely sure you can actually implement it. You may think that we didn't provide enough details about how to implement the GPT. Unless you actually write the code by yourself, there definitely will be some details you will not be think of when we just discuss the concept or the abstract architectures. However, in our particular case, the GPT is more towards the simple side. So what we were going to show you, it is not that difficult to implement the GPT from scratch. I'm going to introduce one implementation by myself that is using numpy, or not using PyTorch or TensorFlow or Keras or other tools, but we start from numpy and we can actually make the GPT work and load the pre-trained weight from OpenAI and do some text generation. I have already done the implementation, but I will try to mimic what I have done before and writing the code using the VS Code. And we are going to have homework set 4. Like I said, I have some concern about the hardware requirement for training a model. So I've settled down on this one. So you are going to using nanoGPT to train a character or byte-level GPT model. We'll cover this one later in today's lecture. So right now I'm showing you the structure of today's lecture. So first we are going to use to talk about the first part of it is using high level of GPT. So I'm going to using high level APIs. Specifically, I'm using the transformer package from Hugging Face to load several models that you can ready to use, including the latest Llama 3 models. I'm going to show you how to load Llama 3 models in your computer, given that you have hardware have enough memory. And also, I'm going to show you how to use the TAIDE, TAIDE, which is Llama 2 fine-tuned by Taiwan's, I think the government supported it to build our own large language models for Taiwanese use. So I'm going to show you how to use these high-level APIs in transformers to very conveniently loading models. Because Hugging Face is so popular, so if some companies are releasing some new models, chances are they are going to release in Hugging Face format. So it will be very possible that you can load this new model using transformers, Hugging Face transformers API. And I will go into a little bit details into the transformer API so that you can understand how it actually works. So you're not going to be intimidated by this. The API is very convenient API, so it is designed to be very abstract. So it is kind of difficult to trace the code. But I'm going to a little bit about it to show you how to trace the code. And second, we are following nanoGPT and nanoGPT implementations. These are very popular educational implementations of GPT. They are simple implementations. We are talking about it, but we are kind of mimic their behavior. So we are going to build GPT-2 implementation, not in PyTorch, in NumPy. Mini-GPT and the nanoGPT are based on PyTorch. So we are doing something different. One way to do that is to implement in Rust or in C. We can actually do that because I actually prepare tutorials of how to do in NumPy stuff in Rust. So that is doable. But for educational purpose, we are going to use numpy because most people are more familiar with Python and numpy. And plus, my plan is to first implement it in numpy, and then I translate the code into JAX. JAX is a deep learning framework developed by Google, which is a bit toward low level compared to TensorFlow or PyTorch, but it is very compatible with numpy. So it is supposed to be easy to port numpy code into JAX. The JAX actually has an interface, so it can mimic the behavior of numpy. It calls jax.numpy. So if everything goes well, maybe I can simply replace the np. I can simply replace the import numpy as np by something like import jax.numpy as np. Maybe it will just work out of box. And then because JAX has the ability to do backpropagation and to track your gradient of each component, and it has already including some optimizer, so I can train the GPT models by using my implementation of numpy. So that's my plan. But what I have already done is doing the inference. So I'm going to show you how to do that. And the third part is to use nanoGPT to train a GPT model. I'm going to include two examples. One is the character level model, that is included in the nanoGPT. Because let me first show you the nanoGPT and min-GPT. So the author is very famous. It is Kapasi. You probably have heard him before, because one of the reasons is because when we introduce the character level models, Kapasi is the author of that blog post. He's the author of this blog post. So we have already seen his work, and he has many implementations of GPT in his website. One is nanoGPT, and the other is min-GPT. And his latest implementation, he's also, I think he's also the author of Llama 2C, but the latest and the most trendy implementation is this one, LM.C. It used C only to implement a GPT or transformer-based model using only C language and CUDA, and it without PyTorch at all, and it reached a very high performance comparable to the performance of PyTorch, and it only used like 1,000 lines or 2,000 lines, which is small. But you are going to see that a lot of these achievements are pretty amazing, and I admire his work. It is not that unreachable. So I can show you, we can do it in numpy from scratch. And you can actually implement all of these things without numpy, just by using like for loop of things. If you will see that it is not that difficult. So the whole purpose is hoping you're not intimidated by the difficulty or you don't need to be intimidated of the architecture of GPT, because behind the scenes, it is actually a very simple architecture that you definitely can understand it totally. Okay, so that's the third part. We are going to train a model by a character level model. And we have two examples. One example is the Shakespeare, and the other one is using a bunch of Chinese novels like Jin Yong or some other novels, because I have already collected them when I do the character level lectures. So I have used them as an example. So chances when you do the autoregressive model homeworks, you have already collected some data set. Maybe you can use them and train the GPT model. So I'm going to show you how to do that. And finally, I'll discuss our the homework. To describe what the requirements of our homework. That's homework 4. So that's today's lecture work, what we'll cover today. So let's begin with the first part, using high-level usage of the models. So first of all, let me first show you the main GPT. Let me try to see. It has a main GPT. Let's start from there. It is more, let me maybe just to search main GPT. Although it kind of archived because the authors has shifting the focus into nanoGPT and LM.C, but I think it is still very educational. If that is our purpose. So this is main GPT. So it actually has a demo GPT notebook to show how to generate the text with main GPT. And here, not only it shows how to use the main GPT implementation, it also shows how to use the transformer implementation to use GPT-2 to generate text. So we'll start from here. We're going to use GPT-2 using transformer API to call the GPT-2 models and generate some text. So where can we find the model? If you search huggingface and the GPT-2, you are going to find the models and which we are going to use when we do our implementations. So you can do the same thing for GPT-3 or Llama. GPT-3, you cannot find the GPT-3, you can find the Llama 2, Llama 3. So for example, here a collection of GPT-2 weights. I believe that the original GPT-2 weights are maybe in TensorFlow format, maybe this one, TF model H5. But here it contains a bunch of different format, several different format converted from the original weights, including PyTorch model, which is a pickle file. So we can actually pickle using the Python pickle module to read the pickle file. But a more popular or modern format is SafeTensor. So that is what we are going to use. And if right now for a high-level API and also for our NumPy implementation, it also has some tokenizer information. So recall that we are going to use, when we use modern generative model of text, it also always use some algorithm like BPE or sentence piece to do tokenization and encoding. So it contains some information about it. So we basically have two phases. One is tokenizer and the other is the generative model. And it also has some like TF-Lite ONCs format of conversion. So if you are cloning this repo, you will download a lot of files, but most of the time you are going to need only one of them. Okay, so let's start it to use the GPT model. Okay, so at the beginning, let me check. Okay, I have already installed Transformer and I actually have already run this code before, so it has already downloaded. So but the code is kind of like this one. From Transformers, import GPT-2 tokenizer and GPT-2 ML head models. It can replace the GPT-2 by auto, but right now I'm going to use these two classes to load our things. And I'm also going to use PyTorch. So using Torch, I'm import two of these things. And let me define our model type. First, I'm going to use GPT-2 XL, which is the largest model of GPT-2 family. And our device, I'm going to use CUDA. Okay. Also, it is a good idea to check whether our CUDA is available. Okay, so in this machine, I actually have RTX 4090 installed. So it has a GPU with 24 gigabytes memory. But you don't need that large memory, and the GPT-2 is relatively small models. So you can actually run it in CPU without many issues. and it is for inference. Okay, then I'm going to first load our models. Let me first load our tokenizer. There are actually two different paradigms to use transformer. One is using a pipeline approach. The other one is using this like the tokenizer and the model. I'm not going to cover the pipeline API today. So just so you know that there's another popular way to using these models, and it may be very convenient. So this is one of the Python API convention that is used by Hugging Face APIs, because the diffuser also has a pipeline since. So maybe we'll cover it later, but today I'm using the tokenizers and the model separately and call them directly. So the convention or pattern for using this tokenizer or model is you start from loading them from pre-train. The pre-train may be in some certain format. It may be a file name. It might be a file name, or it can be a file name, and it can be a repo, and I mean the author and the repo name. And so it is very complicated format, because you know that if it is a repo, it is something like some models like this one. And if you want it to be a file, because a file also has this kind of format. So if you want to load a file in a relative path, so you are going to start with a ./x and y, something like this one. But here we are going to use GPT-2XL. It is not with a slash. It is still going to remote and fetch the file for us. So let me run it. So you're not going to see a progress bar right here, because I have already fetched the file. Some of the model. So if it is the first time you are using this on a machine, then it will show progress bar and downloading the files for you automatically if everything is correct. And some of the file has some restriction, so you need to log into the Hugging Face. So here's Hugging Face CLI login. When you run this one, so of course you have to first register in the Hugging Face website and get a token. Here is a link you have to follow, and from here you can get the token, and you put the token here. It will set the login automatic for you on this machine. So you have to do this for every different machines. Because I have already done it, so I don't have to do it again. Okay, so I have already downloaded it. I don't think GPT-2 is require any login, but there are models that requires you to log in first, like Llama 3 or TAIDE, TAIDE. Next, we are going to load our model here. Okay, so we have loaded our two models already, and I'm going to set the gradient tracking to be false. Because usually you are doing something like with torch.noGrade and the wrong code here. But for all this notebook, we are going to use in evaluation mode. So I'm just setting it to be enabled. We are going to disable gradient tracking totally, gradient tracing totally. So I'm going to say this globally. And I'm also going to set this model into evaluation mode. Because this one is a very small model, so I don't have any trouble I won't worry too much to load it again, because it's really fast. I don't have to load it again, but yeah, it just takes 1 second or two. And I've set it in evaluation mode, and I disable the gradient tracking fully. Some of the model or some of the frameworks will do it for you when you do like this one. When you do the generation, I believe it will disable the gradient tracing for you. But anyway, we are not going to use it. I disable it totally. Okay, so we are already loading our models and the tokenizers. So right now I'm given a random prompt. So you can see that it already auto-complete a prompt right here. This one is a prompt that I'm going to testing our tokenizer, because definitely there are some words that is not legitimate word. So we can see how it encode or decode them. So let me first use the encode tokenizer to encode it. Let me should see the tokenizer. Okay, that is probably just work. So let me should see the encoded input is to be this guy. So what is our encoded input? See, so it is a dictionary, and it has an attention mask, and it has input IDs. So what these IDs are? So let me first to decode this 1212. We can decode it back, but maybe we wish just to decode the first one. So let me just okay, no, this should be after a squeeze. Okay, let me first decode the first one. This is a list. So why not we just loop through this how long it is, like encoded input. Let me first show the shape of it. So it doesn't have a shape. We have to. It is a dictionary. Also, we use the shape of this guy. Okay. So let me see if it works. Okay, it works. So you can simply feed, and you don't have to feed the list into it. You can simply feed a number in it. So you can see the tokens are actually, this is good day. How are you? XY, Y, Jab, AB. So this is how the list guys has been tokenized. So it will look something like this one. And maybe we can show something more, like I here. So you can definitely show that we have 14 tokens. Each of them looks like this one. Okay, so there's also some spatial prompt, like this one. It is a spatial character. End of text. Let's see how does it works. So you can see that it is encoded into one number, because this guy is spatial word that you can use as a beginning of a sentence. So you can start from an empty sentence to generate things from an empty sentence. Okay, so let's generate some text. So let's let our X to be encoded input. Let's make it 3 times and to the device. Our device is CUDA right now, but we can see this. So because we wish to generate 3 different sentences, so let's copy it 3 times. If I wish to generate 5 times, I'll do this one like 5. Okay, then let's generate our text. So let's y equal to model generate x. It already fill in the things for me. Okay, so let me use it. It is actually good what I'm intend to input. But anyway, okay, it is not in the same device because we didn't load our model in CUDA. We can simply transform it into CUDA, but let me check. So let me do it, make it right. Like I said, it is a small model, so I reload it again. Okay, so after the model has been going to the CUDA, so we have generated this text. and we want to print our output. So this is the output of it. It will show everything because it is autoregressive model. So our Y will repeat everything and then generate the rest of things. We have setting the maximum new tokens to be 100. So it will only output 100 tokens at most. And you can see a result right here. So it generated from an empty string. So I'm not going to lie. I'm a sucker for a good story and the start of innocent and ends badly and something like this one. The story, what happened when Obama administration attempts to, and so let's start with something like a question. So we can test why we need instruction fine-tuning. So let our prompt to be what is the highest mountain in the world, and ask it to see if it will actually show the results. So let me remove what? We don't remove, we'll just copy this one and go back here. We don't need these guys. Okay, let's go here, and to see the answers. So we have 5 different answers. Let's see what it actually correct or not. So the first one, the height mountain. So you can see the classical example for why we need instruction fine-tuning. What is the highest the mountain in the world? And it start to writing a poem, the greatest in the world. I do not know which, so this is not what we want. What is the highest mountain in the world? If you said Everest, tell me why. It's kind of correct because this is supposed to be the answer that we want, but it is not in a format that trying to be assistant and answer questions. And it going to, so it started, it looks like a problem set and examples. This one seems to answer the problem correctly. This one is not. It starts to give a bunch of different questions, not simply answer questions, not simply answer a problem. However, even if with this form, we can slightly modify the prompt to kind of making it align with our intention, even without changing the model. That is what we call the in-context learning. So instead of simply asking the question, we give some examples. Because this one is actually the auto-completion and auto-regression models. So we wish to trick it into generating transcript between user and AI assistant, the chat between user and the AI assistant. So if it believes it is generating transcript, so maybe it will generate something more like question and answering things. So I'm making this prompt. First is a description of what is going to be following. Because you can imagine in thousands of data it used, it may contain some transcription. And the transcription, I'm doing my best to describe something might happen in context with a transcript. Also, it says it is a transcription. Maybe I should just say a transcription of something. The following is a transcription of something. But this is what the prompt it is. I actually mimic or giving some non-important conversation between the user and the assistant. So it will give some momentum to the model and some example that the model can see. But I didn't give some information. I only kind of motivate it to generate transcription between user and the assistant. And then I finally ask a question. And not only I ask a question, I also give some prefix of the answer. So the assistant says, sure, the highest mountain, suppose it will finish the sentence and say something, the is whatever it will answer. So let's see, does this strategy works? Okay, so it requires a little bit of time to generate, and we have our results. So let's see the first one. Sure, the highest mountain I knew is Mount Everest. Okay, it doesn't matter what it said later. It actually answered the question. And of course, because we haven't make it stop. If we are building an application, we'll stop at the phrase user with comma, a semicolon. So here, right here, we'll start here, and you can build a chat application, even it is not instruction tuned and it is not chat fine tuned, but even with its current form, if you are going to use it, there's some way to do so. Let's see what is the highest mountain. Sure, the highest mountain in the world. Okay, this one failed. So it is not perfect. We still need instruction fine tuning or chat fine tuning. But maybe I should give it is, and it will doing better. We will see it. We can do the experiment after we check in the results. So sure, the mountain is K2. Not the same, but maybe not correct. But it is an answer. Because maybe K2 is the second highest mountain. I'm not sure. I'm not an expert over this. But if I recall it correctly, it may be the second highest. So if it is so, then the answer is not correct. But it's still trying to answer the question it is wrong answer, but it is answering. And we have this one is Mount Everest, located in the Eastern Hemisphere. I'm not sure it is east or maybe it's not east, but anyway, the high mountain in the world is China. Is it correct? Sure, Everest. Okay. It answers the question. So you can see that out of five answers, four of them at least give some reasonable answers, and three of them might be correct. So let me do a small modification to put it into is right here. And you can see that it's K9 is Mount Everest, and you can see that it's over 2,000 meters high. So it can manage to give some wrong answer, even if we give it the is. But it is still better to answering a question with a question. So it is an improvement, small, but it's an improvement. Okay, and sure, the high Himalayas. Sure, the highest mountain is Mount Everest. Okay, so this is sort of prompt engineering to help us to making our models to do things. So that's, if we wish the models to do things at current stage, there still need to do some prompt engineering is required because the model is still not perfect. But what we are dealing is model that maybe 2 or 3 years ago is GPT-2. So it is not the latest one, but even with the latest one, they're not perfect. You still need to, they're very capable, but on the assumption that you using the right method to get the results. Okay, so let's change our model to be a smaller one, to be the GPT-2. It is a much smaller one, which is the model that we were seeing on the Hugging Face repo. So we'll do pretty much the same thing. The tokenizer is still the same. So we're not going to see the result. It doesn't matter. But for these mountain things, let's see what it will answer. It is super fast. It's much faster than the previous one. But let's see how good it is. It's fast, but what is the quality? Sure, the mountain just after the forest. So it is not good. It is not good. And okay, this one is correct. This one is also correct. Mountain Fuji, sensible answering, but factually wrong. It's NARS. I'm not sure. So it's not in the South Pole. Okay, so it doesn't seem that worse, but you can see that at least it is much faster. Okay, so how does it even works? So first of all, if we wish to, so we're going, no, we're not going to the second part. So we are still in, well, let's further investigate the other more latest model. Then we'll go back here and try to figure out how the model works, the GPT-2 model works by investigating or study the source code of the transformers and try to implement the code by ourselves. It is one way to learn things. I think it is one of the best way to learn things and make sure you understand everything. You implement it by yourself. This is what Feynman says. If you cannot implement it, you do not understand it. So even if the you can see that the transformer is a piece of good engineering, maybe, and it has a lot of layer of abstraction. But we don't have to do those kind of abstraction. We just want to implement the core idea and the algorithm of the GPT-2. So how do we get the core idea of GPT-2 or implementations from this implementation of the transformer? So we have to get through all these layers of abstractions and get the meat of the code. So how do we actually get it? Well, I will show how to do that. And in fact, I believe that the main GPT is doing the exactly same thing, because the code architecture and implementation is very similar to the transformer is. But that's just my guess. I'm not sure about it, because it may refer to the original implementation of using maybe in TensorFlow, maybe, but I don't know. But the code structure is very similar. I mean, the MinGPT, the coding structure of MinGPT and the GPT-2 implementation in transformer are very similar. But anyway, let's go back and use some more capable models. Let's get Llama 3 first. So first, let's get auto tokenizer and auto model for causal LM. This is the model that you should use if you are interested to testing the new language models. So our tokenizer, let's use the Llama 3. You can find out the Llama 3 list in Llama 3 repo, but I'm copy here from my previous code. So I'm checking my previous code. Let me. Okay, it is Meta Llama. So this is a repo name. I believe it will make AMA autocomplete for me. No, it is not. It's not doing. I'm not only using the AB model because I'm not doing quantizations. So, and I only have 24 gigabytes of memory. So even if I'm using 16-bit, I probably will need 16 gigabytes of memory. So if I'm using the largest one, the 70B, I don't have enough GPU to use it. Even if I'm using a 4-bit quantization model, I don't have one. So anyway, we are doing pretty much the same thing, using a tokenizer and using a model. Only we have a different model ID. So I probably just change the model ID. It's equal to, hoping it will be autocomplete for me. Okay, it will do right now. Because I'm going to later I'm going to use the TAIDE, TAIDE. Okay, then I'm going to make the model to device and make it into evaluation mode. Okay, then do we still have? Okay, let me restart it because we are run out of memory. I see. When I load this model, I need to give some, because if I'm using 32-bit floating number, it is not going to work. We don't have enough memory. I'm going to use bfloat 16. Okay, so let me run it again. Okay, it seems to work. And because it has already been fine-tuned for chat instruction, it has instructed. You can see that in the name, it is instruction fine-tuned. So you can give it in a certain format, and we can actually see the model device to see if it is in CUDA. Yes, it is already in CUDA. Although we make it to be auto, it is still in CUDA. So let me use the first example from the Llama repo. I have a bunch of different samples. I mean, copy it at once right here. So I'm going to use the first one and not the rest of them. So this is our message. Okay, so you can see this is the message. We give a row of system and the content. What does it says? The row means who is saying it. The content means what it says. So if we are going to give a chat-like experience for using this model, we can encode our message into this dictionary. But if you see this one, you may think, okay, this is something new. We haven't seen it before. Didn't we just design a model to handle only text data? How did it even go with the dictionary? And how do I know the format of this dictionary? The format is usually provided in the huggingface repo. So you can see the example of the instructions. And also, you can see through the training data of it. It usually uses some common training data. So it's very likely it is using some common format of chatting, to encode a chatting into a certain format. So in fact, you can actually check the code like tokenizer. The tokenizer can apply chat template from message, and we can get these things. Let me get this input IDs is equal to this guy, and let you see the input IDs. So no matter what, we are going to see the model is only taken a sequence of integers, and these integers are the number of the token, the index number of the token only, the ID of the token. So no matter what format it was, it will first combine into a string of text. And we're using a tokenizer to split the string into tokens. And finally, we are given a list of token IDs. And then we send it into a model. So no matter what the format, it looks like a very complicated dictionary. It will always go into something like this one. We can actually see what the text looks like. Let's use the decoder. To see the ID here. Let me print it to make it more pretty. Let me get it here. So you can see, in fact, it has a very interesting format. It is a text with some special command tokens, like this one. Beginning of the text, starter header ID, so it has a header, and end header ID. You are a pirate chatbot who always responds in pirate speak, end of ID. So this is header ID, end header ID. I don't know what it is. EOT ID. This is EOT, end of text, and this is starter header and doing the user. So it actually format it for you. So the dictionary is not designed to intimidate or making things complicated. It is because we know that there are a lot of different possibilities of designing a structured text like this one. You don't have to know it. You're just giving it in a dictionary, you unify the dictionary format, and the tokenizer will handle it for you. But in the end of the day, it will generate a text, and it is not trying to hide the text for you. You can either go to here to see the code. You can go to the code, and maybe you can turn on the debugger to tracing the code and to see how it will actually work, because there's no secret about it. You can see the code, or you can just like to decode the input IDs into text, so you can realize what it looks like. So let us generate the response. Okay, so output is equal to model.generate. Let me copy it from my other notebooks, because this is what works. The terminators are yes, this is correct. The reason I don't let it autocomplete is because it's too long. So so let me print the response. So you can see that as an instruction, it will show talking to you like what parrot would be. My hearty, my name is Captain Chat. So it is in fact following our instruction. So let me try another prompt. I don't have to print it again. So let me put it into one single cells so we can run it in one click. So let me ask some trick questions to it. Sometimes some AI is going to get it wrong. So the question is, I give some instruction that it is intelligent AI assistant, but the question is, I'm asking, so say, I have 3 apples and I put 1 in my left hand. How many apples do I have? If it is just blindly to apply the arithmetics and on these numbers, it may be like 3 plus 1 or 3 minus 1. But if it is truly intelligent, it will answer the question correctly. So let's see what happens. So in the system prompt, I'm asking it to do the inference step by step, like using a chain of thought. But I didn't give an example. I'm just asking it to do this like a zero shot chain of thought. So you can see the result. It doesn't. Last time I checked, it answered it correctly. But this time it is not. If I have 3 apples and I put 1 in my left hand, I still got 3. Let us give it another try, because last time I checked, it did it correctly. Okay, so this one, it got it correct. And it has a habit to say it's a simple question. Maybe in last time it also says, okay, a simple question. But the question is simple, but your answer is not correct. But this one, it got it right. Although I'm not... Okay, this one, the inference steps are in fact also correct. So let me try another one. This one is for car. I have 3 cars and I drove it to a restaurant yesterday. How many cars do I have? You still have 3 cars. It answered correctly. I didn't... the car is not something disposable, so I drove 1 and I lost 1. It's something I can drive yesterday and I can drive today. I still have this one. So it answered correctly. So this one is in Chinese, but let me try to test it with Chinese multi-language capability. This one is math puzzle. It says someone, Xiaoming, this year is 6 years old, and his sister is half of his age. So when Xiaoming is 70 years old, how old is his sister? So let me make it more difficult, because 7 is an odd number. It will tend to get it incorrect when it is even number. Although 70 is, it is even, but 7 is odd. So let me make it 60. So I'm trying to trick the AI to answer 30, something like 30, because half of his age things. So let's see if it will answer it correctly. It answered correct. But I think this one is because they might put this kind of puzzles into their training data. Because people have already tried this sort of questions to test the ability of AI like 2 or 3 years ago. A lot. So yes, it answered correctly. And I have no doubt about it. And another question is like, I bring $300 bills with me and I have to pay a check of $170. How much change am I getting? It is not 300 minus 170 and get 130. It usually, because I only paid with $200 bills, and will keep it one myself and only give these $300 bills. Only give two bills, $200 bills to the setting is in a restaurant, so I'm giving these two bills to the waiter or waitress. So I'm going to get the change of $30. So let's see if it is going to get it correct. So it returns very strange. Maybe get so it still suppose I'm paying it with $300 bills because it most of likely I'm going to give the waiter $200 bill. So let me try it again. Because different time it will have different answers. Oh no, it still got the same answers. It is not totally incorrect because I still have some. I mean, in principle, I could give the waiter $300 bills, but yeah. It seems it consistently reply 130. It is not entirely incorrect, but it does say something. Okay, so I think I still got one Chinese prompt I have already prepared. This one is from the TAIDE, example from TAIDE, TAIDE. It asks the AI agent to translate the following English. Dongshan Cafe is a very famous for its unique position and the constant refinement of the production method. The flavor is admired by many coffee aficionados. Okay, so it asks the AI to translate it into English. So let's see how it does and compared to the TAIDE models. So the instruction is saying that your name is TAIDE and you are helping Taiwanese instead for Taiwanese, and you are going to use traditional Chinese to answer the questions. So here is it will translate the English into Chinese. It seems it is answering in traditional Chinese, and it's correct in translation. Only that the Dongshan it translates it as Dongshan, which seems to be a little bit unusual name for a coffee because we are suppose seeing it as a Dongshan, like a winter mountain or East mountain. It seems more like a name of more common name for things. It gets something like a Dongshan. So but it is still a plausible name for coffee. It's just maybe a little bit unusual. So let's test for IDE. The TIDE is so the model name of TIDE is, let me copy it here. Okay, so the model name. So we have the model name to be the TIDE name. And we can use the auto tokenizer to get it. Because TIDE is based on Llama 2, so you can use the Llama 2 tokenizer and the Llama 2 model for casual. And on the description of the TIDE, it has to use fast has user parameter use fast to be false. This is specifically discussed in the web page repo page of TAIDE. So I'm using this one. So let's see these things and see how it works. Because it is a Llama 2 based, maybe it is more fair to compare with Llama 2 based model. But you can try it. So I'm encouraging you to actually try a lot of different models and see finding any models in Hugging Face. And I mean, if you have enough suitable hardware, you can try it. Or by paying a small amount of money, you can test it on Hugging Face space. I'm not sure Colab can work, but the Colab hardware has at least 16 gigabytes of memory. So it should just work fine. Okay. It's still called it Dongshan Cafe. It doesn't seem to be correct. No? I'm not sure why. But last time I checked, it's called it Dongshan Cafe. It's kind of fun to play with this. models. However, right now I'm going to do the numpy implementations. Let me open a new Python file. Let's call it demo2 file. Okay, so first of all, because we already have runnable implementation, so we can compare our implementation with this one. So we load this model here and the PyTorch one, so that we can compare our implementation with this guy. Okay, so first of all, we can download the model, self-tensor model here. And second, we're going to skip tokenizer. We're going to use the tick tokenizer, which is independent implementation of the tokenizer of GPT-2. Because although tokenizer is not too difficult to implement, it has a lot of different choice in the design of it. So it is very difficult to get it 100% correct to the implementation that you are wishing to mimic. It will need like a lot of time, like 2 or 3 hours or more, to debug and try to test all corner case and see your implementation is actually works. So I'm not trying to do it right now. The main GPT has its own implementation, but I don't think it is 100% correct. And the nanoGPT use tick tokenizer too. So let me import the tick tokenizer. So import tick token. Our encoder is tick tokenizer GPT-2. So let's check they actually encode the same thing. Encode like let's set a prompt is equal to hello, good morning. And we put this prompt into our encoder. Okay, it got this output. And if we use our tokenizer to get this input, and we'll get like the same thing. So it's also always good to check they are the same before we actually use it. It requires a lot of different testing. So you can see that in the implementation of BPE in main GPT, it actually has a lot of test case. It is not in regular, in a more formal, like unit testing framework, but you can see that it comments out a lot of testing cases in its Python file because it is only one file implementation. And we are going to use it. Okay, so what is this model? So first of all, we are trying to load the self-tensor. So how do we actually load the self-tensor weights? If it is a Pico file, we can use Pico, but how do we even load the self-tensor? Let me search on the internet, on the Google, to see what tensor is. So in the huggingface self-tensor, this is the GitHub repo of the self-tensor. We can do that. We can install self-tensors and ask it to do the things for us. It is implemented by using Rust and has a Python API. But it turns out the format of this tensor format is really simple. It starts with 8 bytes. It starts with 8 bytes as an integer. It is unsigned little endian, 6-bit integer, and containing the size of a header. And a header is simply a JSON file encoded in UTF-8, so we can actually read it. Each of the key looks like tensor name and the D type and the shape and where the information is stored. Because in the rest is a buffer. So in this buffer, we need to know the location of the values is stored for this tensor. So that's all we need, and it is simple, but we got every information we have. It only left us to do the implementations. So how do we do the implementations? So let's call this F is open model that save tensor. So we need to put the RB right here because it is a binary file. So first we read first 8 bit because I already put the implementation in this repo. It already got it correctly. So we read 8 bytes from the file, and we have to specify the byte order to be little endian. Endian is that how do we actually represent our integers in byte? There are many different conventions like big endian and little endian. It is in little endian. You have to specify because the default is big endian. So our n, what is our n? This looks like pretty reasonable size. So next we are going to read our header. Before you do that, you can do something like string using the using strings to see the text data into this file. So you can see this is actually indeed a JSON file. If you simply less it, it should just work, but you will get a warning. But you can see that at the beginning is something like this one is 0. On the left right corner, this H at this symbol is 0. That we know that because we read a lot of things, so we know this represents a 0, and this is 7 and C B. So the total should be, because 7, I forget what the ASCII code of 7, but if you maybe 37 or 30 something like that, 37, or in hex or not, I kind of forget. But if you know what the 7 ASCII code of 7 is, you can actually know what the number it is. But we don't need to worry about it because we are using Python to read it and getting it to be the byte order to be little. So then we read the header, and we can see what the header is. Okay, we get dictionary because we have already decoded the JSON file into dictionary of Python. So that's it. We can see like a header, keys. So each one of them might be like the layer name, and you can see a lot of has a dot in it, and one of them is metadata. So let's check what the metadata is. This seems to be a special key, and indeed it is. It is specific in repo of safe tensors. It says it contains a special key called metadata. And other than that, it doesn't have any other special key. All other keys are the name of the layer. So let's see how the metadata is. It doesn't contain much information. It only says the format is PyTorch. The format is in PyTorch. That's it. Other than that, it doesn't have anything. So I have to read everything into a wait. So to save our time, I'm going to copy paste my implementation and explain what it is and why I want to do that. Okay, so let me copy things right here. Okay. So first of all, we read the buffer, read the rest of the content into a byte buffer, and we can check what's the length of. Alternatively, you can, seek the location and read the corresponding part of the things without just reading it at once. It will save some memory. However, the reason that I read it at once is, first of all, it is small. It only has like 100 more, less than 200 megabytes. So it is small. I can handle it in the whole memory. This machine has a 64 gigabytes of memory. So the rule of thumb is that if you usually need like double the size of the file size. If your file is something like 10 megabytes, you probably will need like 20 megabytes to handle it in the memory in most of format. And you probably will require one more puppies to do operations because Python doesn't do things very efficiently. So if the file is something like more than 30% of your memory, or maybe 25% of your memory, you should double think about load it in your memory. But if it is like less than 20% of your memory, it is safe to load in your memory without any thinking, unless you have a lot of files need to be loaded. And in for some file format, because right now we are only reading the file into our memory, but in some file format like Parquet file or they are compressed. So even if a file size is like 100 or 200 megabytes, when you load it with pandas or other package, it will expand into some very large array of things. It will occupy a lot of memory. That's a different thing. But if you only read file into a memory, 20% of memory is a small thing, and you are going to delete them after you use them. But just remember that it is usually required double of the memory if you want to handle it. For now, because we are reading the file into a buffer in our memory, and we are converting a lot of segments of the buffer into a numpy array. So it roughly requires double of the memory. But since it is only like 120 megabytes, it is very small, so I don't need to worry about it. The second thing is for a format. Remember that we got a location. You can see it right here. The location of this guy to say what the position is. The information is stored in the file. This location is relatively to the buffer, the beginning of the buffer, like the buffer we are reading here, not related to the beginning of the file. So if I use, when you want to read certain part, the information of a certain part of the file, you use seek or lseek function to change your head location of reading in the different part of the file. So using seek. The seek is usually relatively to the beginning of the file, or there are three different types. But in our case, the most convenient way is relative to the beginning of the file. So in order to use this information right here, I have to add the length of the header. That is n right here, and 8. So if I want to read them, I need to use this position and plus 8 to get the L6 position. That's a little bit difficult. It's not difficult, it's just complicated and unnecessary. Make the code longer. So I decide to read the buffer at once. And I have already checked every single array of them has a type of F32. So if I write the code by myself, I actually did, but if I write it, I usually just put an assert. Assert the type is F32, and I assume I will read it using the numpy for 32. However, after I type this one first thing, it will automatically give me, I'm using Copilot, so it already gives me everything of it. So I'll take it. I just take it. So this one is a get array. I write a simple function. Originally, I write a code in a loop, but I figured out it will be more packaged more easy and nicely if I put it into a function and I write it into a function. And then the Copilot write this guy for me. So I take it. So basically what we are doing is by given entry of the dictionary. So I get a D type and the shape of it and the offset of it. I read the certain part of the buffer. So I get the beginning and the end from the data offset. And I slice the byte buffer. I get a slice of the byte buffer from begin to end and convert it into numpy array. The numpy provided this utility to convert raw byte buffer into numpy array given D type. It also has other options. It's a from buffer. It has other options to let you to do more fine tuning adjustment to. Then I reshape it into shape because the from buffer always read one-dimensional array. You need to reshape it by yourself. It doesn't consider order. So if the order of the bytes is not in some conventional way, you have to do more work by yourself. But right now, I'm not too worried about it because nowadays, the array, it used to have some Fortran order, C order, or other different order back like 20 or 30 years ago. But right now, people are using pretty much the same order right here. But even if it is not the right order, most of the time you should just do some transpose and permute the index is quite enough. So anyway, this one is the get array I'm getting, and I forget to import numpy. And this one is only check the, because I observed that a lot of keys are start from H. You can see that the keys right here. Let me put it. You probably cannot see it, but you can see H.10, H.2, and each of them has a weight and some of them has a bias. So I see a lot of start with H dot. So I see is there how many of them does not start with H dot. It turns out there are only like 1, 2, 3, 4. The first one is a meta 1, 2, 3, 4, 5. Only five of them, and including the metadata. So most of them starting with H. So I'm getting that guess that the H is probably the transformer block. Everything started with H, and the second index is a number. So maybe the first transformer block and second transformer block and third one. So they're containing the weight of them. Okay, and I'm going to read them into a weight because I have already this one is not. I didn't do it at the first time. I do it after I study and investigate the model of GPT-2, and turns out most of the weight have weight and a bias. Most of the layer have weight and a bias. So I define a new object type called the weights. I use the Python name tuple to do a very lightweight class. So because I don't want to define a when we are doing a simple experiment, I don't want to define some complicated abstraction like define ABC abstract class and derive these things from this class, doing very complicated abstraction. I'm trying to do something more in a more easy, using more like out of shelf collection, like tuple list or dictionary when they are necessary or when needed. But sometimes you need to specify a type which is more useful. In this case, I'm using name tuple because they have the property of tuples, and it is more readable because you can assign the first component of the tuple as W and the second component of the tuple is B. It has its weakness. If you have to develop full stack of deep learning framework or like GPT framework, eventually you probably need to define your class. But for current quick experience, this one is very convenient and useful. And this one is also modified a lot because you can see that the keys of it is something like h dot something, something dot something. It has a dot a lot, contains dot a lot. So I'm guessing this one is some kind of hierarchy. So I'm writing this one to split into a hierarchy, into a multi-level dictionary. Okay, so that's how I did it. So for each key and value, I first split the name into different segments by splitting it into different parts by separated by dot. If it is A.B.C, I will put dictionary B has the value of key B in the dictionary A. First I will, in our root dictionary, I will construct a key A, and the value of A is a dictionary. The dictionary will have a key called B. The B will have a dictionary, will have a key C. The value of C is a dictionary which has a single key D, something like this one. And the D will read the actually array to have its value. So I first split the dictionary, the path name, the tensor name into a hierarchy, a path name, and I will construct a hierarchy. So for each of the root, I will construct the dictionary if it does not exist. So it is really simple. For each child name, at the beginning, I'm using, this is my root dictionary weights. And for each of the child name, I construct new dictionary corresponding to the key. If it does not exist, if it exists, it is okay. But if it is not exist, I'm constructing a new dictionary. And the node is the thing that we are currently at, the dictionary we are currently at. And we're trying to find the next symbol in the split path. So if the next symbol exists, we are going to construct it. If it does not exist, we are going to construct a new dictionary of it. And if it is at the leaf, because we are only walk through the previous path, and the final one, it should contain the real values of the array. So for the last one, we call it a leaf. It's more like a tree. And I will actually get the array and have the name. So it is the last one is a leaf. So this kind of implementation has weakness. Is that what if we have something like x, y dot z, and we also have something like x dot y dot z dot like weight. Let's go just call it W. So if we read the first one right here, we should assign an array to the Z. But at here, we should construct a dictionary because at Z, because it has a child node. It has a child. So we have to construct a dictionary and assign a dictionary to a Z. But fortunately, we don't have to encounter this case. I probably should to add some assertion in here to make sure we didn't encounter this kind of thing. But in our particular case, it doesn't happen per se. And also, I am doing a hack or trick that if a dictionary contains exactly two keys, that is weight and bias, then I will transform it into a name tuple weights into this type. So if it contains exactly the weight and bias, now I will replace this guy from a dictionary into a name tuple. So that will make us more convenient. I don't have to do that, but I have already used these weights. Like I said, I do these things a lot later in the development process. So it is at a later stage. I have already used these weights in many places. It's very convenient. So I have to do this kind of thing. So there are many ways to improve this guy, but well, I'm just reading it into a hierarchy. Okay, so next we have to see what is in fact in our model and to mimic it. So the model, we can simply type model, and you can see that it is a class of GPT-2 LM head model, and it has a child, very important child, which is called a transformer. It is not, the transformer in GPT is not the same as the transformer architecture introduced in the paper. All you need is attention. Attention is all you need. Because in the paper, the transformer is an encoder-decoder architecture. And even with a decoder, it requires some information passed through the encoder. And so that's why it is a decoder. But in GPT, it only uses a transformer block to build its model. And the model is in a more autoregressive manner to train it and use it. But although we call it a transformer, it is in fact a sequence of transformer block. That's it. That's it. So right now, the transformer, originally transformer is a specific architecture. But right now, the usage of transformer is more like we're building things with transformer blocks. Okay, so this one is a transformer. Other than transformer, it also has a child called ML head. This one we will cover it later. This one is a very interesting thing here. But the transformer is a GPT-2 model. We can trace it into it using Visual Studio Code tracing method or in a lot of modern IDEs. I'm using theme key binding. So what I'm typing is GD, go to definition. So I can go to a definition, then I go to a definition right here. So I can go to here and see, okay, so the first one is GPT-2 model and ML head. That's all it has. So what is GPT-2 model? And I go to here and see, okay, it has embedding. WTE, WP. WTE is a token embedding and WP is a position embedding. I'll recall that one is used to encode the token and the other used to encode the position. It has some dropout. Fortunately, we only implement it into inference, so dropout doesn't required because dropout is turned off in the evaluation time. And it has a module list, contains a bunch of GPT-2 blocks. And finally, it has the last layer normalization turn. So because let's go, the most important part in transformer is the GPT-2 block. So let's go to the GPT block and see how does it implement. It has layer normalization 1 and the layer normalization 2. And it also has attention block here. Finally, it has MLP. It has MLP. And we can see the forward. This is forward, and then see how it works. If we have time, we can actually look into it. And another way to do that is using debug feature. You can see that right here. And you can actually type if you want to, let me debug it right here. So suppose we already have these two guys and tokenizer. So how did it actually load the pre-trained model? So if we wish to debug this guy, I press the debug cell right here. So it will go to, because we are using Jupyter interactive shell, so it will go to here. It's not good. So we simply go to the pre-trained model here and set breakpoint at the beginning of what we wish to debug or trace. So it has a lot of, okay, well, I have already said it right here. So let's go back to, and let's run this. This one means continue running until it reaches a break point. Okay. This is because I have already set several breakpoints, so it will encounter right there. Anyway, there are two important things you can use. One is F10. It's like this one, step over. And if you want to trace into this function, you use the step into F11. And you can watch any variable you wish to watch. And you can do any Python expression here to see things. And every local variables you can you can see the value of every local variables right here, even the shape or what it is, and see how it really works. And right here, if you hover your mouse cursor, you can see what is the value of here, because you can see this is static. So at some point it reads everything here, and you can see the keys of the safe tensor, because it actually reads the safe tensor, and we wish to see how it uses this tensor and to fill into the weight and the bias in each layer. So you can see it right here. So it's very helpful for you to trace how and then see how it works. You don't have to guess, okay, whether this if else branch is reached or not. You don't have to guess. Just go into it and follow if I press F10, it will go here. Here is because before we call in the functions, we have to construct each of the parameters. So it will go through here. And if I press F11, it will go into the function itself and go deeper and deeper and see how it works. And when you reach very long running loops, you can use this run step out to run out of this function. It will continue running and will stop when it gets returned out of function. So that is very useful tools that you can use to trace your code, to understand your code. So let me restart it and start over again. So we are in here. Right now, I'm going to show you the code of min GPT. the implementation of min-GPT. So maybe let me check if I have this one. I'm guessing I have. Okay, here. So to save time, we are referencing to the min-GPT code to see how it works. After all, it is the purpose of this repo because it is very for educational purpose. So in the model here, this is the attention block, causal self-attention, and so we are going to transformer block, and we see it has a layer normalization, attention, and a layer normalization too. By going into attention, we can see how it implemented it. So I'm going to show you the first one, layer normalization. We are trying to mimic the behavior of layer normalization and how to do it more efficiently. Given that we have already a runnable example. Okay, so okay, so we already have everything here and get things in right here. Okay, so first of all, we have our models. We can go into our model and see everything. And we know that it has H. No, it's a transformer. The transformer is also a GPT-2 model, and it has H. Each H has like H, say the first one. The first one is H0, and we can see how many parameters it has. I only want to see the length, how many of it. So it has 12. In this transformer block, the first transformer block, GPT-2 block, it has 12 parameter. It most usually comes with pair, weight and the bias pair. So that's why you define a name tuple before. So there are 6 layers has weight. You can see that it is a convolution 1, convolution 1D, these 2 convolution, and 2 layer normalization. And finally, we have fully connected, this MLT we have fully connected, and the projection. The number seems to be correct. We can actually, like this one, to see how many parameters are in the MLP. It has 4. Right, we have 2 pairs of parameters. And how many parameters are in layer normalization? They are weight and bias. Okay, so let's see what the weight and bias is. Okay, we simply type. Let's just see the shape. Do not see the 4 things. The weight is like, does it have bias? Okay. I say that I don't want to see the whole values because it is just a mess, but I actually show that. But anyway, the size of weight and the bias are both of them are 768. So what our guess is our loading, the array that we loaded from the safe tensor is exactly the value here. So let's just check. So, it has also already auto-completed it. I'm waiting to see the W and the weight. You can see, okay, they have the same size. I have the same shape, but how about the value? So I'm going to compare with it. So it already auto-completed with for me to convert it to a numpy array. So let's first check that. Okay. I forget to do one thing that I mentioned that I have to do. I usually do it at the very beginning. So because we are using evaluation, so I should set this one to save our some trouble. So anyway, let's do it over again. So we got all true, but there are too many truths that we cannot handle. So what we want to see is it's all true. Yes, all of them are true. So they are exactly the same array. Please note that sometimes because the precision of the float point, it is always in general tricky to compare floating numbers. So if it returns not true, don't give up quickly. You want to check whether they are almost the same. There are many ways to check how float number is the same. The simplest way is to minus with them and find the absolute difference. And if they are small enough, then they are fine. There are also numpy function to check two arrays equal with some tolerance. That's the thing that you can use. But here, and one important thing is that NaN is always NP NaN. NaN is always not equal to NaN. So if your array contains some, even though they are in the same position, it will not the same. It will not equal to each other. So it requires some consideration, and there are some functions to help you to do so. But usually you can also use the subtraction method to do the things like this one. But need to be careful, because if you're using a like this one, whether this is less than, you're going to get a false. So be really careful about floating numbers. Okay, so they are the same. Mostly because we are loading from the same safe tensor. We haven't do any operations yet, so they are probably won't differ that much. To be sure, to be safe, let's compare the bias. Yeah, also true. So now we are trying to do the to mimic the behavior of layer normalization. Okay, so you can see that we have WB here. So that's the convenience of using a weight, because it is a tuple, so we can extract it using the tuple destruction method. Okay, so we don't have enough. Maybe we'll because this is a video, so and although it is streaming, it will have a video recording, so you can check it later. So I'm going to finish it anyway, even if it is overtime. So let's say this is WB right here. We'll get a WB. Let's make random input. So XPT is equal to torch random. Do we need that much things? So the reason is that the first number is a batch size. The second one is sequence length. And this one is embedding. We know that our embedding is this guy. You need to look at it, but I already know the thing is this one. You can do the forward, I mean the transformer or for the whole model. You can trace it into it and see the shape. That's one way to do that. Or you can do a more brute force or more barbarian ways to do that, to put the print function into the model itself and print the shape out of the whole model, to modify the source and print the shape. I still often do that in many cases. It has some advantage, but if you want to do a more modern and a civilization civilized way. You can use the debugger to trace into the function and see it. But the print or logging way has its advantage because it actually logs the results, so you can look through the result. But if it is just a one-shot thing, you might want just trace into the function and see the result. Okay, anyway, we got random XPT. I'm pretty sure it is what we want to do. So we got a YPT to be model dot. So that's for convenience. Let's say our ln is equal to, let's just say that our layer, because the way I'm trying to do is I will try to mimic the behavior of attention, everything, embedding. I'll do all of them separately first, then I will put them together. So it is more generic name is layer because I'm going to change the layer into another different kind of layer. Transformer that, but for now we are going to use the first layer. Here, this is our layer. The layer normalization is our first layer. So we can call it in and get into a, although it is dubious to call it YPT because we are converted into a numpy, but this PT means the result generated using the PyTorch function. You can go to it to see, and this is actually the torch, maybe .nn layer norm. So you can check the web page. There's a document of the layer normalization and tell you how it works. It always works the last dimension. Okay, so it is we're trying to do a normalization. So we are doing this guy x minus x dot min and divided it by x std. Now this is what we call the normalized x. Then okay, we should do it at the last axis, and we have to keep our dimension because if we don't have the keep dimension is become assigned to be true, then it will reduce the last dimension to become, right now it is 110 and this one, and after you do that it will become 110. We wish it to become 110 1. Okay, the mean is the same. To keep the dimension the same, it will better suited for to make the broadcasting work, or the dimension broadcasting works. And then we are times to our W and plus our B. I'm not sure W and B dimension works right, but it seems works fine on the last dimension. So we got our things. So this is our Y. So let's see what Y is and what YPT is. They look similar, not the same, but similar. It seems the interpretation is correct. If you are not correct, you are trying to figure out more and make this one correct. Go to the source code or do more guessing and how it works. Maybe you use a different axis and see what happens. But it's just a small job. You are going to make it correct. So I'm going to compare these two guys using the absolute value and see the maxima. We are not expecting them to be the same, so we're not even trying to compare the equality, because a floating number is, especially we are only using a single precision number, have very limited precision. So it will usually have, if you add the floating number in different order or time them, do a multiplication in different order, it will yield different results. That's nature. So if the difference is small, then that's fine. So the difference actually is small, but our number is not big. So maybe we should try something like division. Okay, -1, make sure -1. Compare different one. So it is larger than this one, but still like less than 1%. This is not good, but acceptable. We are hoping it to be a little bit smaller, but this is probably what we can get so far. And for single precision, this one is acceptable. And because language model is kind of noise resistant, so we know that this kind of noise, we know we are doing it correct. Just because the numerical instability, so it will have a different result. If we wish to have to verify more, we should use double precision and see it. Because we are dealing with a lot of different numbers. So the errors is going to be accumulate. We are using a 32-bit floating number. You know that 3 digits is like 10 bits. So 20-bit is like 6 digits. So 6 digits is probably, because we're not using all the 32 bits to do the precision, we have to do exponent and do the sign. 1 for the sign and some for the exponent. So like 6 digits precision is very common, or is very typical in the precision of single precision number. So this is a precision or error that you can allow. But we have like thousands of number collected, so to accumulate the errors. So this one is the errors that because what we are trying to do is to do the mean. So we are doing a lot of different addition and do here. And also, because of the numerical stabilities, the layer normalization also usually has epsilon number to avoid division by 0 things. So let's probably just go to the layer normalization page that you can see. Okay, so I'm getting a page and I'm dragging it right here. So this one is in fact formula. So we got the weight and the beta right, but we also has an epsilon. We should put the epsilon right here. So instead of using the standard deviation directly, we should put the variation here and plus epsilon and minus the, let's just code the formula here. So we do the variation. The epsilon, default epsilon in the GPT is 1 over -1 power to -5. And so EPS, and we do square root here. We could use mass square root, but we use the NP version. We cannot use, we should use the NP version. Okay, and we see the differences. So the differences is reduced to like 1 in 10,000, 1 over 10,000. So it's greatly reduced. So that's probably it using these things. So you have to do this thing a lot. Let me try to finish these whole implementations. Okay, let me check a thing that I already wrote it here. Okay, so I put it into a class. Right here, it is into a class like a layer normalization. For two reasons. One is it mimics the behavior like in Keras, in PyTorch, each layer is in a class. It keeps the code more clean. So because we are keeping the weight inside this layer. And this weight is, well, I use the type hints to show this one is a weight and given default epsilon. And the code is used for like the forward for in PyTorch, but I use the code directly because this is a very simple usage. We don't have to track many different things. And I use a trick that tuple deconstruction to get the weight and this formula is exactly the same as this one and return the things right here. This is layer normalization. And similarly, I can define linear. Okay, I can define linear. Let me check is this entirely correct. Yeah, this is correct. So for linear, it is easy. I have checked this one is actually works and consistent with the behavior. So the definition in the PyTorch linear layer. And also I have something called embedding. Although embedding is not too difficult to implement, let me first put the embedding right here. I don't have to copy it because just like the auto copilot to do the rest of the work. I'm just checking on my other screen. This thing is actually doing right. No, it does not doing things right. So embedding can be written in a very convenient way in Python, syntax in Python, using a fancy indexing. So what the embedding is, we given a sequence like 1, 2, 3, 4, 5, and we checking the rows or columns of the embedding matrix and taking that row out of it. So for example, let me get an embedding. Yeah, I can get an embedding WPE. Let me just get a WPE. So it didn't hurt me by saying WPE. It's giving me a WTE. So let the WP to be a WPE. So the shape of W is the weight. I need to get the because the context window is only 1024. 1K, it has only 1K context window. So that's why it only have 100. So the position will only have 1024 positions. So each one has an encoding of 768. So if we want to encode embedding, get an embedding of the like 3, 4, 5, 6, we simply put it into the index, then we get things like this one. The shape of this guy is 768. So we have 4 elements, and this is a sequence, the length of the sequence, and this is the embedding of each one. So because of the syntax of the fancy index syntax of numpy, it is very easy to write down it even without define a class of embedding, because it's not easy. But we are trying to do this to mimic the full framework so that we can use it as an API and write the final works in a similar way. But you can see that it's even the linear is a very light wrap for Python functions. Especially we have already, this one is not a weight because this one is simply a numpy array. So we have to make it to a right type hint. So the good thing is if you put it into a batch, it also works. So we have make it a batch of 1. So you can still keep the batch. So this one is totally works out of box as an embedding. And also we can define some activation function, like the activation function used in GPT is GLU. So we are using it right here. Let me check if it is correct. Yes, it seems to be correct. Pause. Maybe I should just copy it. Because I cannot fully check the correctness of this guy. Okay. Maybe I should use the one that I just put here. So this one is a formula of GLU, and we also define a softmax. Okay, softmax. Is it correct? X. Let me still using my. Okay. Let me just copy my implementation, just in case that there is something wrong, because it's very difficult to debug if it gets something incorrect. So basically, we are trying to making it more numerically stable because instead of using A directly, I'm using A minus the maxima of it. Otherwise, if some of A are really, really big, the exponential is going to be really, really big. And it will kind of difficult to compute, especially if you are using some smaller type of floating numbers. It will easily to make exponential to blow up. On the other hand, if something is really small, it doesn't matter because the small thing is going to 0. That's fine. That's fine. I only care about the big guys, not the small guys. So I'm making the big guys to 0 and small guys to negative things. If it is really negative, that's fine. It's getting the 0. Okay. So the final piece is the self-attention. About everything is pretty easy and straightforward. The final piece is the self-attention. I'm going to copy it directly here because it is more complicated case. So this is our self-attention model. The class of self-attention. These are just some things that checking the dimension of the weight is correct, is compatible with the actual things. And okay, so let me explain it line by line. So our initialize routine construct getting a linear. We are getting a linear weight. So this one is actually linear. This is attention, and another is a projection, which will come back later. And we define the number of head and the head dimension. So we don't have much weight. We have only the initial projection from the previous layer. And then we want to project into a key, query, and a value. And then we are having finally we have a mask. So I have two kind of linear layers, and a mask and other things are not trainable. The mask is just masking things before we are only refer to, because we are using an autoregressive model, we only refer to the previous steps. So we are having a mask. So this mask, this error seems to be very mysterious, but TI means triangle. So we are considering a triangular matrix. But there are many different triangle matrix. Upper triangle, lower triangle, left, right triangular. This one is a lower triangular. So because it is triangular, so it can give a mask of the you can only refer to the previous items, not the future items. So we're using, when coding these things, we are destructing, using tuple destruction to get a weight and bias, to give it a short name W1, B1, W2, B2. So at the beginning, when we get an input here, the input is something has the dimension. Let me put the dimension here. It's something like 1 sequence length and 786. So let me just put the sequence length to be like 5. It's a small sequence, but it is more readable. Maybe not. This is batch size. Okay, because I already used right here. So after doing the first projection, what is the dimension that I'm getting? Y is, let me put a comma here. No, this is not 700, and this is times 3, because we are going to split into key, query, and value. So in the description, we are having 3 different linear projector. One for key, one for query, and one for the value. But however, because we are using a self-attention, and we can do it at one run, and split the result into, just the 3 different things. Each of them have a dimension of different things. So we use the NP split into 3 equal parts. So each of them right here, each of them will have I'm using Q for example. It will have batch size, sequence length, and 768. Because we have evenly split them into 3 parts. And finally, I probably should put it. We should put it. Well, I'm putting a result here. And what is this thing do? This is doing to make it to be a multi-head. So although this one is a very really high dimension, 768, it actually contains the dimensions, embeddings of different heads. This is just not one head, it's a different head. So the dimension of this one is the number of heads, and we first, before we do the, you can see the 2 heads that we do the transpose. Before we do the transpose, the dimension of it is like this guy. Number of heads, and the heads dimension. So number of heads is 12, and the heads dimension is 64. So 12 times 64 is 768. So we actually just simply split this 768 dimension into 12 times 64. And we do transpose to move the number of heads right here and the sequence length right here. Because we are doing the attention separately for each batch, for each number of heads. So we put them at the beginning. It doesn't matter that much in our implementation, because you will see that when we do the attention map, it is sort of the dot product, but we have to keep the batch size and let's share the batch size and the number of heads. Both of them are kind of number for batch. So it is not typical dot product. It is some kind of matrix multiplication, some kind of dot product, but it is a batch matrix multiplication. So we were writing the formula in the paper or in presentation. We are writing it as a matrix multiplication, but it is in fact. Let me check the YouTube. Still working. Okay. So we are writing it in formula as a matrix multiplication, but in fact they are batched matrix multiplications. So that's the small things, but kind of the things that you need to be concerned when you do the implementation, because you don't have the function. You don't actually have the function. Okay, let me put my reference code on another string. Okay, here. So we are using the Einstein summation to describe this kind of thing in general. So let me put it in more bigger size to focus on this guy. This means the first, because we're doing the Q, doing some product on Q and K, query and key. The first 4 number define the dimension, the index of each axis, give it a name, BHMD. B means short for batch size, H means for number of heads, and M and the sequence length. Although because we are doing a several attention, we know that they are same, but they are different because it is the first length. In principle, they can be different. And the length is for the sequence for a query, and N is for the sequence for the key. Also, we have BHMD. D is the dimension, or the embedding dimension, which is 64, and the H is 12. In our current case, in most of our current cases, the base size is 1, and in our sequence length is M is 5, both M and N 5. So after we're describing the index BHMD and BHND, we are going to define the dimension of the output. So we have a BH, they are same as the BH here and the BH here. B and H here and the B and H here. So we certainly know this one is going to be the batch index in a batch index. So that's no problem. They are going to use in a batch. And because we have MD here and ND here, and we have M here, we know that D is a dimension that we are going to connect to match it together when they're doing match multiplication. So in traditionally, we are doing something like MDDM, MDDN to MN. So this is a typical matrix multiplication. MDDN, and the D is kind of eliminated because they are the same. We can do the dot product on this dimension and keep the M dimension and N dimension. So I have N pairs of dot production. But in the Einstein summation, you don't worry about the order. You can actually put this one. The meaning of this production, this multiplication is still very clear and mistakable. So you get this one. So this is what we want. So we simply describe this multiplication and get what we want. And then you recall that in attention is all you need pep. It has scale right here, np dot square and the size of head dimension. So we do that here. And then we're doing a mask. The mask is, recall that how the mask work. If it is not in a mask, if it is a future element, we fill it with negative infinity. So the exponential of negative infinity is going to be 0. That's what we want it to be. So since we have a mask right here, we expand the dimension into dimension compatible with the attention map, which is the batch size and the head dimension. We could do this at the beginning, and maybe we should. Let's do it. So how will we do it right here? So maybe we just square. Okay. It is more clear to put it, although they have the same effect. Okay, so but anyway, you have to make it into, because our sequence length is not 120. I mean 1024. So you have to kind of cut it into a small one. So we cut into a small size right here. I'm not sure if we simply reconstruct it using np.trl. Maybe it is equally fast. But anyway, this is what we do, and it works. So we are contracting it, and we still need this kind of cutoff and slicing. And we work it on our attention map. So if it is on the mask, we are keeping attention map. If it is not, we are replacing it by a negative infinite. Then we do the softmax on the last dimension. And we are combining the value. Recall that we are mixing up, using the attention map to do the weighted summation, weighted average on the value. This is also written as a metric product, but it is a batched metric product. So we use the Einstein summation notation again. So we have the BH, MN, and the BH, ND, and finally we got a BH, MD. M is the sequence length, and D is the embedding dimension. So we are getting a dimension right here. So here, our Y is going to be base size, number of heads, sequence length, and head dimension. Yes, it is the head dimension. Okay. Then we want to transpose it and getting something like the concatenate everything together. So now we get the base size, sequence length, and the 768. Recall that the number of heads times number of dimension is equal to this guy. So we get this one, and we get our result. So we begin with some tensor with dimension, batch size, sequence length, and the embedding dimension. And turns out we get something with the batch size, sequence length, and the embedding dimension. Exactly the same shape, and getting this out. So this is our attention layer. Okay, so finally we have to put everything together to get a transformer block. So the transformer block look like this one. Because we have already done all the hard work, this one looks very similar to the implementation of nanoGPT. Although we are using numpy, we don't use any PyTorch. We are only using numpy. This one looks, especially the following one, looks exactly the forward function of nanoGPT. So what we are doing? We're doing the first layer normalization. And we doing attention map, self-attention. And because we have residual secure connection, we plus the original X. And this one is actually a trick, because if we put this separately, we are going to to use another variable to recall the X and the output of the middle output and the final output. But because we are putting them in just a single line, the X is intact, at least before this assignment is doing. So we can put it in a single line. And finally, we do this normal level. For the output of this attention block, attention layer, we pass the X through layer normalization. And then we are going to put it through MLP, multi-layer perceptron. So this perceptron has two layers. One is FC. One is called a CFC. One is called a C project. This is also come from the same name, from the weight, from the self-tensor weight file. So we use their weights, so we don't have to assign the dimensions, but they are just simply doing the things to get the right, give us to get to the right right of dimension of everything. There are just some MLP. So recall that we need an MLP to as nonlinear things. So we got this NLP right here. Just a simple two-layer NLP. Okay, so we got our block and our everything, self-attention and everything. We need to construct our GPT model. This is in fact equivalent to the GPT transformer and plus the GPT LM head model in the transformer implementation. Okay, let me copy it. The GPT right here. So we have, this is very similar to the definition of the GPT LM head and the GPT transformer, but I put them together. So the first 1, 2, 3, 4 lines. I should put the okay. I should put them here. Okay, this can be auto computed from the weight here, especially from the okay. I probably don't need to put a head and a head dimension here because did I use it? Oh yeah. I'm definitely need to use, because the shape of the weight doesn't have enough information, but I only need one of them because the head times the head dimension is the same as the but I also need the N layer can be auto computed because this is exactly the same as the length of the this guy. But the head and the head dimension, let me just specify it. So we have the first, this embedding the same as the definition in the GPT model, which is a dot transformer in the GPT ML head. And also F is also in the transformer. But in the ML head, GPT ML head, it also has a head. But interesting thing is it doesn't has a key called the ML head in self-tensor because this one is using the same matrix as the WTE, the token embedder. So the ML head is using the token embedder. Wait, again here. In the mean GPT implementation, it doesn't solve this problem. It simply asks transformer, the huggingface transformer, to load the GPT model for him, and he acquired weights values from the GPT model. But now I'm not even using the self-tensor module. I'm using only the numpy and using the open file to open file function in Python, the built-in open function to open the file and read the file and get everything by myself. So I have to handle this. Then the thing is pretty straightforward. So we give a position encoding. So given length of a sequence, we find the position encoding and do the encoding, embedding, finding an embedding. And then we're doing, for each block, we are feeding this embedding into this block. And finally, we are feeding it into a layer normalization and feed it into the LM head or language model head. And we are done. Okay, and we are getting the last output. Leo means Leo is the batch number. Because we only have one batch, so we just get the first element out of here. And -1 means we are taking the last hidden state. We are only using last hidden state and get the logic right here. Because we haven't do the softmax yet, so we are only using a logic. So right now, let's load our GPT. And for GPT-2, and let's try to see if it actually works. So for GPT-2, these are the parameters. We have 12 layers of blocks, 12 transformer blocks, and a multi-head of 12 heads, and the embedding size is this guy. And the head dimension is related to the embedding and the number of heads. And then we control our GPT model. Our GPT model is with number of heads and the head dimension. Let me just check fitting it correctly and see if we are missing anything. Okay, it seems fine. Then we are given a prompt. We're not going to give it too difficult question. Okay, what is the highest mountain in the world? Well, if we are doing it correctly, it is exactly like the GPT-2, the smaller one, GPT-2 model. And we are getting encoding is equal to, let's see, the encoder is a list. You probably not it is just a list, a Python list, not even NumPy. It's just a Python list, and we are designed it to have taking a single list as input because the implementation is pretty slow on a GPU, on a CPU in one thread, so it is very slow. So let's run the while here. Incorrect. Okay. What is incorrect? Let me see. What? Return WX or WTE plus WPE. Okay, let me debug it a little bit. We can actually do a GPT WTE to see which one, because it is X or GPT. Okay, then we see a GPT W. This one is WTE. Wait. This one is a name tuple embedding, what does embedding? Weight, it has a weight. You should call it weights, but it's called weight. That's my bad. It is a numpy. Okay, so it has a shape directly. Okay, so it is weight. No, nothing wrong here. What is our x? So it is not wrong, but this one does not work. Let me try to see what. Okay, I see what's going on here. I know. That's why we always need to copy it without using. There's always something you can go wrong. So it should be something like this one. Okay, so let's do it again. Okay, it works. It is a small time of, so we can, let's see what y is. Y is not in, you can see that is just an array, and the array has a shape of very large array. We should do a softmax to do a sampling. So I have to do a sampling. So let me try a sampling process right here. So I'm writing it in a loop to let you see the, I'm not doing the top K, I'm doing the temperature sampling. I'm not using top K, top P. I'm simply using the temperature. And you can see how it works. It will generate one token one by one and see the most important thing, the apex. It says the highest mountain is the apex. It actually doing quite well. It's answering the question. And we should do the print the decoded. It's actually doing quite well. What is the highest mountain in the world? It answers the apex, and it goes again to do more examples. Okay, because of the time, I have to stop right here. Otherwise, it can go very long because there are a lot of details. But I hope I'm not finished the lecture yet because there are the training part and the homework part. I have to explain. That will be a little bit quickly in this one. But the development it and the reconstruction from scratch part, I'm going to stop right here. There are a lot of things going on and a lot of details I can share about it, but going to start it, and hopefully it can get you started to have to understand, have a way to really understand using Feynman's method. If I cannot implement it, I do not understand it in the spirit of Feynman's idea. And actually it's workable. It's not just idealism or a fantasy or fiction. You can actually implement things to make sure you understand it. There are times that even if you're doing this many times, you are pretty sure I'm understand everything. So I don't have to implement it again. But in many cases, there are something that you overlooked. Some small details you overlooked. It is very likely. So by doing this kind of reconstruct things from scratch, it's going to help you a lot. Like if you are studying the operating system, you are learning the machine language, you are learning a lot of different, like how the website work, how a web framework work, how a database work. You probably can implement yourself a virtual machine, operating system, maybe a database, a web framework, that is going to let you feel that you really understand it. Okay, so the next thing we should do is to use the nanoGPT and do in training. So you have to clone the nanoGPT. Let me go to a page. So because this one is still newer repo, so I can find it right here. So this one is nanoGPT. So you can give a star if you wish, and I think it really deserves your star. And it will tell you how to install it, and how to prepare your dataset. We are using Shakespeare character dataset for example. So you can do exactly what it does. And after you have output, then you should edit the file here. It has a configuration of how to train it, like how many layers does it has. And if you don't have a GPU, you should use the GPU. Colab, use a T4, that is quite enough because the training is really fast. I can actually do the training right now and let you to see what happens. But I have to go to Visual Studio Code that I have. Let me go to the Visual Studio Code. Which one? Okay, this one. Oh, no. Okay. One bad thing about the Visual Studio Code is the title bar is too crowded. When the window is small, it makes it difficult to drag it. You're likely to accidentally hit some buttons. So just what happens. So take time to drag it here. But anyway, this is something that you can. This is my modification of the transcript so that you can see what happens during the training. So let me do it right here. I'm using my train 2 so that you can visualize the training process a little bit. So you can see it is using only a 6 layer of transformer block, using only a very small dataset it prepared before, and I have already prepared. Just using to read the Python file for data preparation. It will generate everything. Basically, it just translates every character or every byte into an index number and put it into a binary file. But okay. Oh, okay, I see. Let me use the original one. You cannot see the process, but it will save some time because I haven't tried to use it on the original Shakespeare. I'm using it on my dataset, so it will differently. But it will be very fast, and I will show you how to construct a sample notebook that showing the output. So you see that it trans very fast. That each iteration is like 17 milliseconds. And you can adjust. Let me go to the config and see the config of this guy. It has a config right here. Train Shakespeare character here. Remember that we are using the character level and the byte level things. So There's another one for the fine-tuning Shakespeare. We are not doing this one. We're doing the train Shakespeare with character level. And you can see that it defines how many rounds, how many iterations it is using 5,000 iterations. So you see that it will stop at the iteration 5,000. And you can see the loss. The loss is cross entropy, so it makes some meaning to you. So you can check and see how well it works if you are trying to when you're trying to adjust your network architecture. So right now it is using a baby GPT model, which means a very small GPT model, only 6 layers and 6 heads, and embedding size is 384. So it's quite a small one. We're almost done. So I'm using it on GPU, but if you are using CPU or slower GPU, you are going to get more time for when you train it. But it's still going to be not too many time. And you can actually even reduce the size of the model a little bit. Okay, after we have already trained it, we can there has some instruction on the website to tell you a suggestion of how to reduce the complexity of the model. You can take that, or you can try it yourself if you don't have enough hardware. But since it is really quick, I will guess it is quite enough to use the Colab GPU. It's very enough to train this model in this phone. If you have a better hardware and if you are willing to, you have more time to use the Colab, then you can train more complicated model or train it with a larger data set with more iterations and use this loss value to adjust your model. You probably should check it with the validation loss and the training loss all together to see them all together. But yeah, so you can make sure that it is not overfitted. Because if your dataset is very small, it is going to be overfitted very quickly. So this one is the Shakespeare, and this is sample file. So you should put your sample generating file to streamline this PY file, or to take what it needed to generate things, put in your notebook file, and generate some text from the trained model in your homework. So right now it uses the tick token and use the implementation here, nanoGPT, and it set everything here. And I'm assign it the LDR directory here. In the original usage, it has a line that read command line argument. I remove that line and assign the directory right here. And you can copy everything here, or you can just choose this init from resume here and get the weight. Put a model into device that's pretty similar, and I compile a model to make it faster. And the good thing about this implementation, it contains enough metadata, so no matter how you modify the code, it can read the data from information from metadata and get everything right, including the tokenizer things. Okay, so right now I'm giving a start to be quite empty, just a single new line, and we can see what happens here. Okay, so this one is generated. You can see a lot of things generated by our models. You can specify how many tokens you are going to new token you are going to generate. But in any case, you can see the generated quality is pretty good. So GPT is in general really good at generate readable text, but it doesn't, as for these small models, even for big models, the reasoning or logic is usually the difficult part. So you always generate something looks like grammarly correct, but it is difficult to generate something more consistent in logic or in the meaning. Okay, so this is one thing you can do. I don't believe this model can, if we feed the prompt of like what we feed it into a GPT-2 or in the Llama 3, it will answer them correctly. Like asking how many apples in your hand, or how many cars do you have, or even asking what is the highest mountain in the world. I don't think it works, but maybe we can try. Okay, what is the meaning of life? Okay, this one seems good enough. So let's see. Does it answer anything related? Okay, it gets something like I never saw brief. Okay, it looks like something related. Next one, I'm going to show an example of training not using the Chinese character and how I do it in byte-level. So first of all, I am given a prepare function. I'm building a new directory and copy the prepare function from the Shakespeare example. Then I copy some of the code from my demo in the lecture that I do the character level things. So I read everything here. But instead of using, like I said, this is using a simplified Chinese, and I convert it using the OpenCC to traditional Chinese. And so you can see that when I decode it in GB encoding and encode it into UTF-8 and convert it into traditional Chinese, and I encode it into UTF-8. So everything is in UTF-8. So let me run it a little bit. So because I have already encoded in UTF-8, so since in training dataset is something like this one, you can see it is, you cannot see. But you can see here, it is some like machine code, because this is what the UTF-8 is. I can decode them back to the Chinese, like decode. And I probably have to put ignore. I mean, when it encounter error, it just simply ignore, because it probably have cut the sequence in a wrong place. But we can encode the Chinese character into a byte series. So I'm working on the byte. So each Chinese character is corresponding to 3 different bytes. If you are using a big 5 encoding, each Chinese character is corresponding to 2 bytes. But in UTF-8, at least for traditional Chinese character, each of them are encoded related to 3 bytes. But I'm not working on a character, I'm working on bytes. So it is even a challenge for the model to produce valid Unicode that represent Chinese character or any meaningful character, because it reads something like XE2. X means hex, X in hex representations. So this E2 is a number, 80 is a number. So I correct all these things and doing translation so that each encoding is mapping to a index number. So the code is pretty simple, but they have already written by the copycats here. So you can just simply use them. So the whole data set, the character data set, I mean the whole vocabulary, we have a data set of 168. The folk vocabulary is like this one, like A, B, C, D, F, like all English letters and all this machine code, like that used in Unicode representations. And finally, they use this information to build string to integer and integer to string. But the thing is, because we are working bytes, not strings, it originally consider everything is working on string, a text and a string, but we are working on bytes. So you have to modify the functions accordingly. Otherwise, it doesn't work. But I think this one is, let's prepare. Yes, this one should be works just fine because I have already done it before. But you need to be very careful about these kind of things. So we have a huge data set and we can do the training and it will save the things into files. So that's what you should do. And after all of them, it will save it into a file. So I put it into my interactive way into Visual Studio Code and I run it line by line so that I can understand what it was doing and so that I can modify and make it doing the things I wish it to do. Let me show you the training process. First, let me show you results that might do when that might be sample 3, I guess. When I use this into a lot of, to show you the result. So this one is sample 3. So I tell him that my output directly is out ZH character, and rest of things are pretty much similar, but the decoder and the encoder need to be modified so that it can handle with the bytes, and also it need to be decoded from UTF-8 into something that you can display. Okay, everything works just fine. And I give an initial. Yang Guo says something, and I first encode it into UTF-8 so that because the model works with bytes, so I have to encode it and getting the IDs. And after the model is only work on integers. It doesn't care about bytes, character, or anything else. Then it generates things. So if it works good, it will become some like what he says. So you can see that it always kind of like conversation between guys. Maybe because the novels in Gurong always have lots of conversations. So after it, although this character is from Jin-Yong, but when it says something, it usually replied by some character from the Gurong novels, Gurong's fictions. That's pretty interesting. And of course, you can generate things. And you can see that the generative qualities, at least in grammar or text writing properties, is much better than character level models that we used. The variety and everything is also better than the model that more likely not the LSTM model you have trained. So you can see that every segment of things seems to be quite reasonable text that appears in some segment of a fiction. But although you look into it, you will see some inconsistencies, like different characters from different fictions, different fiction world, fictional fantasy world, fictional word. Okay, so that's the result, but the thing I really wanted to show you is the training. So let's see a train 2 here. It doesn't matter maximum iterations. It will take a little bit longer because the size is bigger. Okay, but you will see that at the beginning, the sample generated text is totally unreadable. You can see that because in principle, it only reads bytes, and the bytes doesn't easily get to be UTF-8. It needs a lot of luck to put random bytes to become a valid UTF-8 representation. So you can see that at the beginning, it will generate something really like error or machine error or garbage code. But after just one step, like 200, maybe just one episode, you can say that, it will get something much better. Much better. At least it learns how to encode things correctly in that at least UTF-8 can recognize. It can generate valid UTF-8 representation of Chinese character. So before it can generate some meaningful text, it should can generate meaningful character. That's the important thing at the first step. So after it generates pretty good at the character level, it will become better and better. You can see the loss is getting lower and lower, and the sentence is still not quite there yet compared to what we see in the sample that we just show you in the inference, but it is getting better and better. But also, because we are using a byte level, so the loss should be much smaller than the character level, because character usually has a larger vocabulary size. The larger vocabulary size usually related to the larger loss. The smaller vocabulary size will correlated to the smaller cross entropy loss. So, but you can see that even with these very small little steps, it will get something. This is something. Consider we're starting from a totally random garbage output. So this one is the motivation. I modified the training script a little bit so that it can show you us some results when it's saving its checkpoint. It will also show some sample results so that we can monitoring the progress of our model. Okay, so that's the part of training. So let's go back to homework part. So let me describe how the requirement of homework. So the homework is check character level GPT model or byte level GPT model. So we are asking you to train a model that doesn't require any tokenizer. So you can do any, you don't need to use BPE or any fancy tokenizer. You can use JBA or other things to get reasonable vocabulary size. Presumably, you can use just any files, because any files we can read bytes by bytes. If you use in a binary mode, we can read bytes. So it might be a GIF file, a picture file, maybe a MIDI file, maybe even PDF file, or any executable file, any files. You can use, if you have those in your hand or you want to collect them, you can use them as your training data. Okay, so maybe I should just see it in the web page. Okay, let me go to web page. So the homework is right at description right here. Oh no, this is homework 3. If you haven't done it yet, then yeah, it's already expired. It's homework 4. Okay, so I can make it larger. So the first thing is download the nanoGPT and modify the code and train things from scratch. You can try to fine-tune the model. It is also a good experience, but there are many different ways to fine-tune a model. So I think it's more like a good experience for you for homework is to train it from scratch. So I choose this setting. And build your own data set. That's important. You have to build up your test of what kind of data set works and how should I modify the architecture to make things even better. So one thing is that because we're using the byte level, so the context window probably should be bigger, because in the general setting, in the most typical setting, a token may contain one word or many words. Even if it's just a subword, it will be significant portion of the word. But most of the time, it contains one word or maybe even more word. But in our case, 3 tokens equal to 1 Chinese character if you are doing the Chinese things. If you are doing the English things, it's not getting better because 1 English word contains many characters, like 3, 4, or 5 characters. So you probably need a bigger or larger context window before it can actually see far enough to see things. The other thing is the embedding size. Because our vocabulary is really small, does it make sense to have a large embedding like a 768 if we only have like 100 different vocabulary in our so we just have 100 vocabulary and we're embedding into a 768 dimension? That does not really make sense, because even if we are using 1 hot encoding, we only need like 100 dimension. But because the embedding is using in the whole transformer blocks, so it does make sense. It does make sense because we probably need to carry more information in our character, like capturing the surrounding differences into this representation during the architecture, during the middle hidden states. So probably need those dimensions, especially for a Chinese character. You need that dimension. But at the beginning, the embedding area, probably you don't need that much. So that is probably one thing that you can modify your architecture. And since we already know that the meaning or the real meaning is kind of sparse in the sequence length, so it might make sense to reduce the sequence length. I'm not suggesting you to do this in this homework, but that are the things that you can think of. So at the very beginning, you probably should just use the default setting, because the baby GPT is actually tuned quite well. It is a very surprisingly good in that small size. But a little bit later, maybe you should adjust the parameters, meta parameters, according to your data set. And then you probably want to modify the architecture if you have already confident enough to. Maybe you have some idea, some hypothesis. You can modify the network a little bit to verify or disprove your hypothesis. So anyway, you should collect your own data and modify the things. So the one data set you cannot use is the Shakespeare, because the whole purpose is ask you to collect things and try to have some imagination of how do I started with small project. So you're probably at some point, or maybe right now, you are working on a big project. It is always good practice to split this big project or big problem into small pieces of problem in order to solve them. You rarely can solve a problem in one step. You always split the problem into some small steps. However, these small steps are usually quite boring, and because they are just part of it, a lot of people doesn't make this small step to be self-contained. So the trick is you split the big problem into several ones. This is a technique that is very already challenging to a lot of people. But one thing you should do first is split the big problem into small one, so we can divide and conquer. But the trick is to make small steps interesting. They are not just small steps that can help you to solve a big problem, big picture. Make the small problem a little bit interesting, so you can have some fun with this to solve this small problem. So this is one thing. We are only trying to understand the whole technology behind the large language model and the all generative AI. This is a big picture. So this one is just a small step to understand some of the architecture. So try to make these things fun by finding some application using this toy model or toy implementations, just to make fun. That will help you to understand it more easily, because you can find out more and more issues. If you don't have something that you are interested in, you will have no idea to adjust these toy models. Because although we call it toy model, it is GPT. It is kind of SOTA like 3 years ago. So, but still, you make it more interesting and have fun with it. So it is a good. So it is one of the major purpose to collect and build your own data set. So for Chinese text, you can use either UTF-8 or Big 5. Big 5 has an advantage that each character only contains 2 bytes. So it might make the training a little bit easier if you are focusing only on traditional Chinese character. If you are working on a more variety things, like you are putting some emoji text into, then you probably need to consider the whole UTF. There are a lot of different things you can collect. For text data, you can collect Wikipedia, or maybe using some of the collected data sets that people already collected, like pajamas, red pajamas, those kind of things, and find some interesting part that you can use. But it is not limited to it. You can also use the computer to generate some text. Like, for example, given a description of a graph, like in Graphics, then you generate the SVG. SVG is a text file. Or given a title, you generate the HTML of a website. Sort of things like that. You can do that. Or you can do something like solving a problem, like sorting problem. Like there's an example in nanoGPT, it's doing the sorting. But you can do the sorting step by step, because the GPT only has a very limited context window, at least for this baby GPT or GPT-2. But a lot of things you can use, a lot of algorithms only need to be needed for a very small look back window. You don't need to look the whole data set. You only need to look a very small size of the window. And sometimes you are solving it in a time series, the state, like a reinforced learning. You are doing it step by step. Every time you are working on current state, the state is usually a finite state. So can be fit into a context window. So maybe in this context window, so like a sorting, maybe like a bubble sort, you probably should just recall the pointer of the current ordering and which element you are working on. And maybe this is enough hint to let the GPT know how to go to the next step. And if you are given it enough training data, maybe the GPT is going to figure out the step of bubbling sort. Or maybe you can split like a number multiplication into step by step using school method of doing the multiplication. So by writing down the multiplication step, you can generate it automatically because it is very algorithmic. So you can generate step by step working draft of calculating the multiplication of two numbers as a string. So maybe the GPT can learn it. So there are a lot of fun things that you can try, or maybe like a game of life. You give the surrounding description. You can determine which the cell is going to be alive or going to be dead in next step. And you can feed it in like a binary file, like say a PDF file, maybe more structured things like a LaTeX file, TML, Wikipedia, like Wikipedia using XML file. So maybe you can give a title and let the GPT to generate the content. So those kind of things are all kind of interesting. So you can find out a small project you can do by training these things. And the only limit is do not use Shakespeare. You can include it in a small part of it. Do not copy and use the example. And you probably, in this homework, you are required to use a character or byte-level. This is because there has a lot. It's kind of avoiding you or to prevent you, help you to escape from some easy trap, because most of example doing on the token level. So if you are doing token level, you probably will find something that is very easy to do without thinking to do, and will maybe not that easy because you have to set up the environment, something like that. You still have a challenge, but not the challenges that I am intended to give you in this homework. This homework is not supposed to be difficult, but there still have some challenges that I am intended that you can experience about it. And modify, after your first success round, you have already passed the homework, but just like all other homeworks, it encourages you to do more modification to get a quality. Some students are saying that they are trying to improve the result to get better, but unfortunately, because it takes too longer to do the training, so it cannot return the homework in time. So that is kind of a trade-off. If you making your result better, you probably are getting a better score in your homework. But if you are late, you are probably have some deduction. If you are not late too much, the deduction might be tiny little bit. But that's something you should consider about it. But I'm not going to give you any serious pressure. So if you are trying something and look something okay and legitimate and not directly copy some existing example, then you are passing for this homework. So when you return your homework, you are, as usual, return it in a Jupyter notebook form. Simply describe, just use a markdown. Use a markdown to describe the data set. How do you collect the data? It's a character level or byte level, and the length and the vocabulary size. And your training setting, so you can get the metadata or training setting. You can simply copy the setting in your config train Python files. That's fine, just in a cell. And then you should using sampling to extract the require a component from the sampling PY and generate several different sentences. So your notebook is runnable, except perhaps the training setting. You can put it in a markdown and the code in a code block. But the last generated thing that is runnable, except because we don't have you don't have to return the checkpoint. So we can actually run it, but you should run it and generate the sentence as a proof that your model actually works, and let us know how well your model works. So in order to impress us, then you probably should carefully choosing some prompt, prefix prompt, some prompt prefix. It is a prompt, but it is just a prefix to demonstrate the uniqueness and the quality and interestingness of your work. So maybe you are using a JPEG file or image file. So do not, if you are generating some image file, do not show the machine code of the byte of the generated JPEG. You can show that, but you also have to show the image so that we can see the actually generated image. So that will be perfect. If you are doing some LaTeX, generate some LaTeX, you can also attach or actually generate the PDF file generated by the LaTeX. If you are generating some HTML or SVG, show the sense. If you are using MIDI files, show the MIDI generated image, or maybe record it into audio file to show your work. Okay, so that's it for today's lecture. So because we are not going to, I didn't edit the file. It is all streaming, so it is getting a bit longer. So, but I hope you can practice the stuff that we are talking about and get the totally fulfilling confidence about what GPT is.